I'll spend a little more time working with these Kc equations and talking about the chemistry that's going on in equilibrium. All right, you're interested in the decomposition of cyclobutane by the following reaction. C4H8 as cyclobutane becomes 2C2H4. At 273 Kelvin, 4.0 moles of C4H8 is added to a 1.0 liter container. After equilibrium is reached, 0.214 moles of C2H4 is present. What is the value of Kc for this reaction? So you're interested in the decomposition of cyclobutane by the following reaction. C4H8 becomes 2C2H4. At 273 Kelvin, 4 moles of C4H8 is added to 1.0 liter container. After equilibrium is reached, 0.214 moles of C2H4 is present. What is the value of Kc for this reaction? All right, so we want to know what are we after in this problem? We are after what is the value of Kc. So that means I want an actual number, right? So I want a number to come out of this, the actual value of it. And so if I want to get the number for Kc, the question would be, well, what's my equation for Kc? How can I relate that? And we know that the equation for Kc is based around whatever the reaction equation is, the chemical equation we have up here. So I can go ahead and write that out. I know in this case, Kc, we know it's always going to be that ratio product at the top, so C2H4, and that's the 2, and those are both gases, so they both show up, and over that is C4H8. Okay, so we've got our equation, and we just need to plug in values for these two things. So again, this is the equilibrium constant, so we're going to want the concentrations of both of my gases at equilibrium. And so we can see we have amounts. So we can see, we want concentrations. This isn't a liter container, so moles divided by liters would give me my molarity. And we can see we're given that after equilibrium is reached, I have 0.214 moles of C2H4. So we know that for C2H4, we're good to go because these concentrations should be at equilibrium. So that's going to be the 0.214 moles divided by 1 liter to turn it into a molarity. That'd be good to go. If I look at C4H8, I am given an amount of moles, right? I have these 4.0 moles, and that is added to the container, but then equilibrium is reached. So this 4 moles cannot get plugged into here. I don't just have 4 moles right away or at equilibrium. It's 4 moles initially that undergoes some reaction, undergoes some changes. So what I need to figure out is how much C4H8 is present at equilibrium. And so the way in which the amount of C4H8 has changed is it's turned into C2H4 based on this equation. So not all of it, but some of it has become product. So at equilibrium, we're going to have both some leftover reactant and some formed product. So we can use stoichiometry to figure out basically if we formed this much C2H4, we can figure out how much of the C4H8 actually reacted. So what we can do, we need to figure out the amount of C4H8 that reacted. And we can use just our stoichiometry relationships. We know that we formed 0.214 moles of the product, so that had to come from reactant. So I have 0.214 moles of C2H4. And we know that based on the reaction coefficients, 2 moles of C2H4 comes from 1 mole of C4H8. So if I do that out, that tells me that 0.107 moles of C4H8 reacted. So I added 4 moles initially, then some amount reacted and became C2H4, and that amount was exactly 0.107. So we can't use stoichiometry and say 4 became 8 or 10, but we can figure out the actual relationship is still based around these stoichiometric coefficients. So this is a number, this is the amount that reacted, but we want the amount at equilibrium. So the amount at equilibrium is going to be equal to my initial minus the reacted. And so the initial, that's those 4.0 moles of C4H8 minus the 0.107 moles of C4H8 that reacted. So that tells me that at equilibrium, I'm going to have 3.893 moles of C4H8. So I put 4 moles into the box. Some of them reacted, leaving some amount left over. And so this value, 3.893, is what I can go ahead and plug into my KC equation. That's the amount of C4H8 that I want to put into my KC equation. So I can go ahead and do that, rewrite. I know that KC for this reaction is the concentration of C2H4 squared divided by the concentration of C4H8. So I can plug in values. My C2H4 was 0.214 moles of C2H4 divided by 1 liter. Square that. And then I just calculated my C4H8 was 3.893 moles of C4H8 divided by 1.0 liter. And the 1 liters don't affect it, but it is technically molarities, so we do want to include that in there. And overall, my number, if I put all that together, my value for Kc that I will get for this reaction at this temperature is 0.0117. And so we can fully describe what's going on. We know where we started, the initial kind of mixture. We know we can kind of probe equilibrium, and we can kind of relate all of these different values via this equilibrium constant equation. So we can get these Kc values. This is a real kind of situation where if you know information about equilibrium, you can figure out the equilibrium constant, and Kc 0.0117. So that's less than 1, which means we know this is a reactant favored equilibrium. If you have C4H8, it tends to stay C4H8, not react. But it does to some extent, right? It is reactant favored, but some product does still form. Okay, so this is a case where we're going to need to use this sort of equilibrium description if we want to know what's going on. If we just say, well, it's reactant favored, don't need to worry about it, that's a problem, especially if you want all of that C4H8 or if you don't want any C2H4, right? That's a change in kind of the chemistry of what's in your sample. This is just happening, so we need to take it into account. We need to have that equilibrium description to really see all of the chemistry that's happening. We want to spend a little bit of time talking about this reaction in the context of some kind of how we've discussed or thought about reactions in chemistry happening previously. So C4H8 becomes 2C2H4. So, we could imagine you have 4 moles of C4H8. How much C2H4 can you make, right? We put it in a box, we put it in a reaction vessel, it's going to react. How much can you make? And this is where we would use stoichiometry, right? We can use the reaction coefficients and we can do these calculations, and you can make a maximum of 8 moles of C2H4, right? That is what you could do if all of your molecules reacted.
We could also imagine we've looked at things that are more static. C4H8 is a gas. We could treat it as an ideal gas. So suppose you had 4 moles of C4H8 to a 1.0 liter container. What's the pressure, right? And we could use the ideal gas law, PV equals nRT. So we've looked and described chemical systems before and just kind of said, written down kind of by the power of the pen, either like the chemistry happens or the chemistry doesn't, no chemistry happens, right? And we've just kind of said, made these kind of declarations just by saying these things happen, making assumptions. But the chemistry just happens how it's gonna actually happen in real life. And so Kc is some value, 0.0117 in this case. And so in reality, some ethylene molecules form. Not a ton of ethylene molecules, you're not getting the full conversion. You can only use this sort of pure stoichiometry, just multiply it by the reaction coefficients if Kc is really big. Generally greater than 1,000, a lot of times more like millions, billions. 0.01, not big enough. This is, again, a reactant-favored equilibrium. The reactant mostly stays unchanged. It's mostly just the original cyclobutane molecules floating around in your box still. But you can't just use, say, the ideal gas law, assuming you only have C4H8. These molecules do some chemistry. And so when you make these sort of assumptions of, we put C4H8 in a box, it's going to stay C4H8. That's only if K is small. And this isn't huge at 0.01, but it needs to be like 0.0001. Okay, so in these sorts of ideas of equilibrium is kind of how chemistry really happens. These reactions just kind of happen. There is some sort of mix, and we need to treat them in a realistic way. Everything we've talked about before has been idealized. And a lot of chemistry does happen in that way. A lot of things, you can use, there's a lot of reactions that we care about that have really big Ks. And there's plenty of molecules that are very unreactive that have really small Ks where this works just fine. But we want to be mindful of when we have situations where Kc isn't quite so clean, the behavior of our molecules is a little bit dirtier, a little bit messier, and we do have to worry about this equilibrium description. All right, one more video left in the set. Looking for any more questions on participation 925. See you in that final video.